So how is everyone today? Okay. So, let's see. No, it's not the 26th. It's the 27th. So, last time we were talking about compositional inverse, and we're still talking about that. So I want to sort of remind you of the context of where we are. So, you know, for the 10th time or whatever, I'll remind you that there's this thing called addition that we do with numbers. We can take two numbers and combine them with addition to get another number. Now that operation has something called an identity. What is the identity of addition? Zero. Sort of, you know, as sort of a place to anchor your understanding. Identity is the thing that you could add, and it doesn't require an undo button, right? So undoing addition of 0 is not necessary because it didn't do anything. Which reals have an additive inverse? All of them, right? They all do. So, for example, the undo for add 9 is add -9, or if you like, subtract 9. What's the formula for additive inverse?
If x is negative x.
Negative x, right? So whatever it is that you're doing, you're given, you negate it. Which is to say that if you're given an x, then the additive inverse is negative x. Okay. So we've got addition. The identity is 0. All numbers have an additive inverse, and the formula is negation. So in sort of a very strong way, I want to just look at these. Just have a look at this and say, okay, well, addition is kind of easy. We can just more or less say it all right there. Okay. Multiplication is a little more complicated. Of course, it's denoted by dot. What's the identity of multiplication? 1. Because multiplication by 1 requires no undo button, right? It doesn't actually do anything. Which reals have a multiplicative inverse? Right. So now it's not all of them. It's all reals except 0.
I almost put x does not equal. One of those questions we had that. I almost wrote all reals, comma x does not equal 0. Is
that's fine.
That's appropriate word.
Yeah. So again, to see why this is the case, the question can be stated like, well, if you're going to multiply by a number, what numbers can you undo that with? So if you multiply by 2/5, you can undo that by multiplying by 5/2. Or you could say it like this: if you multiply by 7, you can undo that by dividing by 7. But multiplication by 0 cannot be undone, because once you multiply by 0, you have a 0, and there's no telling what gave you that 0, right? It could have been 13 multiplied by 0. It could have been 14 multiplied by 0. Who knows? Fine. So then, if we have a non-zero x, what is the formula for its multiplicative inverse? Reciprocal. Which is to say that whatever x you're given, the multiplicative inverse is 1 over x. And of course, 1 over x is only defined when x is non-zero. So again, multiplication is to some extent sort of straightforward, but it's definitely more complicated than addition. For at least the reason that every addition can be undone, but not every multiplication can be undone. And notably, we're not even, you know, I'm interested in saying these things because it helps me give you some context, some structural context of what we're talking about, but we're not actually talking about these. We're actually talking about composition, which is denoted with open circle. So up here, when we're talking about addition, the kinds of things that we're talking about are numbers. We're talking about real numbers. And here, when we're talking about multiplication, the kind of thing that we're talking about is numbers. But here, when we're talking about composition, what kind of things are we talking about? Functions. So you've got to, you know, I want to make sure that you understand that the analogy goes far, but only so far. So what is the identity of composition? So in the first place, what kind of thing should it be? Is it going to be a number?
No, it's another function.
It's got to be a function, right?
I still don't know how to see it.
Well, just like the identity for addition is, the way you symbolize it is with a 0. The identity of multiplication is symbolized with a 1. The identity for this, for composition, is symbolized with ID. That's how it's written. Then you've got to remember that, well, ID is a function, so you need to know what its formula is. So ID of x is x. So the identity of composition is a function called ID, and as a formula, it is the function that takes an x and gives you an x. So it is like a conveyor belt. It doesn't do anything with the input. It just gives you whatever input you give. It gives you that output. So now, we did this 2 lectures ago, at least. Identity, and then now the next question is well, which functions have a compositional inverse? This is what we did last time. The answer to this question. The injective functions. Now, in our class, the most common way to confirm or deny that something is injective is to look at its plot and do what?
Horizontal line test?
The horizontal line test. So which functions have a compositional inverse? The injective ones do. Okay. So now, again, with this structure here, for addition, we said, what's the identity? 0. Which ones have an additive inverse? All of them. What's the formula? Negation. For multiplication, what's the identity? 1. Which of them have a multiplicative inverse? All of them but 0. What's the formula? Reciprocal. For function composition, what's the identity? This function that we're calling identity is the identity. Which functions have a compositional inverse? The injective ones do. And here we are. Formula. This is what we're doing today. So does everybody see where we are? Okay. That being said, I want to remind you a little bit about the horizontal line test. So here's 3 functions, or 3 plots. and the prompt is which ones of these pass the horizontal line test. So how about the left one?
Not the left one.
Okay. So you're saying that this one fails?
Correct.
Okay. Why does it fail? Okay. And how can you see that?
You can run your pencil over it and see if it interacts with the
Okay. Good.
plot.
Right. Because the horizontal line test says that a function is injective if every horizontal line crosses it 0 or 1 times. Yet you can see that for this function, here's a horizontal line that crosses it 3 times. So this fails the horizontal line test. Fails the horizontal line test. As a result, is this function injective or not? It is not injective. Which is to say that this function, does it have a compositional inverse? It does not. It does not. You can think of that like meaning something like this is a process that can't be undone. Like if we do this, then there's no going back. Like multiplying by 0. So you couldn't undo this. How about this one? Does this one pass? It does pass. Okay, because again, the horizontal line test says that the plot of a function represents an injective. Represents an injective function when every horizontal line crosses 0 or 1 times. So you can see that in your mind's eye, grab hold of this. There's always going to be 0 or 1. So this passes horizontal line test. This, is it injective or not? It is injective. And how about this one?
Doesn't make sense to ask.
Doesn't make sense to ask. Not a function, therefore it doesn't make sense to ask.
And the reason it's not a function is because it doesn't pass the vertical.
That's right. So it's like exceedingly important to be able to know when it makes sense to ask a question, right? Because it does happen that you might be in a business situation, and we might be talking about tens of thousands or hundreds of thousands of dollars, and someone could be saying like, I wonder if we could do this, this, and that. And in some cases, either the person who offered the possibility of that isn't aware of all the details or hasn't thought it out fully. It's very important to be able to say that actually what you just suggested doesn't make any sense for these reasons, right? And the reason why that's really important is because, well, you don't want to commit hundreds of thousands of dollars to an endeavor that is actually nonsense, right? So it doesn't even make sense to ask if this passes the horizontal line test. Good. Any questions about it? So we've got to figure out how to compute the compositional inverse. So this is by analogy to me saying, like, if I gave you a 5 and I said, what's the additive inverse of 5? Negative 5, right? It's with essentially no work, you just say, well, it's negative 5. The way you can tell that it really is the additive inverse is because when you add 5 and negative 5, you get 0, which is the additive identity. So we're going to do exactly the same thing analogous thing, but with composition. Okay. Let f of x be 13 multiplied by the cube root of x minus 14 plus 8, like so. Okay. The instruction is find / compute f inverse of x. That is to say, the compositional inverse of f. Okay, and then I'll say parenthetically, you may assume it exists. So now, just a brief explanation of why I am saying that is that, well, not every function has a compositional inverse. So strictly speaking, it doesn't make sense to begin finding it without establishing in the first place that it exists. So practicing mathematicians kind of have this thing that to the general public appears like a tick. You know, like we have to always establish that something exists before we want to talk about it. And if this was like a 4,000 level course, you know, I'd give exercises where I say let f be such and such, find its inverse, but maybe it doesn't even have one, and I'm expecting the student to say, actually, it doesn't have one for these reasons. But I'm not doing that in this level. If I say find the inverse, then there is one. Yeah.
Odd question.
Yeah.
If that were just the square root, not
Yeah.
the cube root, I could just assume that it doesn't have one.
It would have one actually, because remember last time when I think you're remembering last time when we were dealing with square and square root, and do you remember that to establish that two things are inverses, you've got to compose them in both orders, and in fact, in one of the orders it worked. If this were square root, it would have an inverse.
It's not square inside already.
Right, it's the squaring one that doesn't have an inverse. In the same kind of way that doing the dishes is the post inverse of messing up the kitchen, but not the pre-inverse.
Because the graph, the plot of this, if it were squared, the square root of the square root of a number passes the horizontal line test.
Exactly. In your mind's eye, imagine what square root looks like. Does it pass the horizontal line test? It does. But the squaring function, the parabola, does not. So once you find the inverse, once you have found the inverse, show that f inverse really is the compositional inverse. So there's just one way to do that. How do you show that two functions really are compositional inverses of each other? Yeah, you compose them in both orders and show that you get the compositional identity in both cases. Okay. So this is the first time that we're doing this. But I want to emphasize sort of conceptually what it is that we're doing. If I had given you the number 13 divided by 14 and said find its multiplicative inverse, well, it would be the reciprocal of that, right? 14 over 13. And then okay, show me that it really is. Well, then you'd multiply it and show me that you get 1. And you wouldn't have to do it in both orders because multiplication commutes, so it doesn't matter. But that's what we're doing. So we have to do some kind of calculation for this. The calculation proceeds in steps. It's kind of like a process. So we'll take f. The first thing you do is you replace you replace f of x with any other variable that you like. So we besides x, right? So you could replace it with y or w or whatever you like. I'll just use y, doesn't matter, as long as it's not x. So we do it. Okay. Next, we're going to solve for x. Now, conceptually, what I want you to see is that what this represents right here, this is the output y of f of x in terms of the input x. So what we're saying is that if your input is x, you're going to use this formula to make the output y. So it's sort of like looking at a diagram of what this machine's going to do when you give it an x. So now what I'm saying is that we're going to solve for x. That is to say that, well, the input is x. So we want to see if we can express the input in terms of the output. This is like if we had a vending machine that was in a locked closet and we were watching people come out of the vending machine closet with their candy bars and trying to figure out what button they pressed. We're trying to work backwards. So we want to express we want to express x in terms of y. Okay, so we want to solve for x. The first thing that we'll do is add 8 to both sides. So then we'll have, sorry, not add, subtract. So we'll have y minus 8 is 13 multiplied by cube root x minus 14. Already dealt with the 8. Okay, now what? Divide by 13. So all of that over 13. And then cube root x minus 14. Okay. Now what? Okay. I agree, but I want to say it slightly differently, I think. So notice that from here to here, in a sense, the 8 changed sides. So what I want you to see is that this sort of looks like, from here to here, it is like we took the equation w is equal to z plus 8. Now suppose that we want that, we want to get z by itself. And we want w to stay on its side. And we want z to stay on its side. So w's going to stay over there, and z is going to stay over there. And what we want is the 8 to change sides. So what becomes of the 8 when it changes sides? Over here it's add 8.
It's negated.
Over there it's subtract 8, right? Or if you like, add the negation of 8. So what I want you to see is it's like when the 8 changes sides, it does it like so. Similarly, we had an equation right there that sort of looked like w is equal to 13 multiplied by z, like so. And if we want the 13 to change sides, but we want w and z to remain where they are. So we've got w stays on the left, z stays on the right, and you want the 13 to change sides. If on the right side it's multiply by 13, then what is it on the left? Divide by 13. Okay, so now finally, this was the question I'm asking about. Structurally, this equation is like this one. It is like we have W is the cube root of Z. And we want the cube root to change sides. We want W to stay on its side. We want Z to stay on its side. So when the cube root changes sides to the left, what does it become? It becomes cube.
So we want to leave the x minus 14 in this cube fraction.
Right. So all the various operations that we do, they all have this, right? So you've got a thing. The operation is adding 8. To get it to be on the other side, you've got to know all these things, like the identity and things like that. You know, we say subtract 8, but really what it is it's adding negative 8. Right here it's multiply by 13, and then we say divide by 13. Well, yes, but you know, from maybe a more abstract point of view, it's saying, well, on this side it's multiply by 13, on this side it's multiply by 1 over 13, because those are multiplicative inverses of each other.
I think I'm missing the point. Like, I'm
Yeah?
not quite sure why you kind of made those clarifications after what he said. Like, I don't quite understand what you're saying is the difference between what he said and what we just did.
What I'm trying to, well, my intention is for you to see that that there's an overall structure and pattern to all of these, that they all fit into the same pattern. I agree with exactly with what he said, that on the right side it's cube root, and to get it to go to the other side it's cube. Okay, so like this. And then the 14 gets moved over. Like so. So now, this one right here, what it was, you know, conceptually you can think of it as the output, y, is expressed in terms of the input, x. That's what this one is. What's this one?
The opposite.
The opposite, right? Now you have the input, x, is expressed in terms of the output, y. So now,
This new term is g of x.
I'm sorry?
This new term is g of x.
Not quite, not a G. We're going to call it, but it is a new thing. We're going to eventually call it this. So I'd like for you to imagine, you know, this is not the way vending machines work in real life, but you know, it's conceivable, I think, that you could, you know, press a button, and then a candy bar comes out, and then you might say, no, that's not the one. You push the candy bar back in, and then the button becomes unpushed, right? It's like a vending machine that can be run in reverse. What I'm saying is that, you know, this is like putting the candy bar back in. Or if you like to look at it a different way, if we witnessed somebody come out of the vending machine closet, and we didn't see what button they pressed, but we did see the candy bar that they came out with, then that's enough information to tell us which button they pressed. Well, if they came out with the Snickers, they definitely pressed button number 5, conceptually. So now what we're going to do is we're going to swap x and y. That is to say, we're going to write exactly this formula. We're going to write exactly this formula, yet when we copy it down, everywhere we see a y, we're going to write x, and everywhere we see an x, we're going to write y. And then finally, the answer is that the inverse function is exactly this. You know, for those that helps, where some kind of conceptual thing helps, it is like saying, okay, the conveyor belt's been running, has been running left to right, and now this swapping step is, oh, I'm going to hit the toggle button, and now it's running the other way. Yes? What?
In the beginning, you replace the x with y, and then in the end, you swap it.
Why do you do isolate x?
Because in the end, the reciprocal doesn't have anything to do with y. That's not what he's asking. He's asking what's the inverse. Why have that to do?
Y is, yeah, Y is just a name for the output. That's all that it is. And so now you can think of it, you know, from here to here. Now it's replaced Y with F inverse, like that. So again, this is like turning the machine around. Okay. So now this is the claim. This is like saying this would be as if I gave you the number 13 over 14, and I said, please calculate the multiplicative inverse, and then you do a page full of calculation and say, it's 14 over 13. Okay. Now I need you to show me that it really is the compositional inverse. So now we have to compose. So I'll do F inverse first. So I'll do F composed with F inverse. And then evaluate at X. Okay. So then writing this without the composition operator, this would be F of F inverse of X, like so. So who is going to see X first? F or F inverse? F inverse sees it first. Okay, so what I'm going to do is I'm going to look at F's formula. So there's F's formula. What I'm going to do is I'm going to copy down exactly that formula, except everywhere that I see an X, I'm going to write a slot, an empty place where I can substitute something in. So it'll be 13 multiplied by the cube root of, so now I see an X, so I'll write, okay, this slot here, and then minus 14, add 8. So that's just a blank spot for me to write whatever the input was, and then I look up here and say, oh, the input is F inverse. So I need to write F inverse right here. Now, F inverse, the alleged, right? F inverse is this. So now I need to copy that formula in there. So then now subtract 14, then outside add 8. Okay. So now, because the instruction was to compute F inverse, and we did it, you know, what is it that we need to, what needs to happen from here onward? What do we need to arrive at? Just X, right? Because you know, we've said that we computed the inverse, so that if you compose these two machines, if you feed an input to first one then the other, then it should be just like a conveyor belt. If you give it an x, then x should come out on the other side. So these square parentheses can be dropped because of the associative property, so then the 14s cancel. Okay, so the 14s cancel. Now what? Not yet. They're too far apart. I mean, I agree that eventually they will, but they're too far apart. The cube root and the cube, right? Because whatever it is I'm covering up, you know, if I'm covering up a 2, we're saying, okay, first take that 2 and cube it, and then after you've done that, follow that up immediately by cube root. So do cube and cube root cancel?
Yes.
In all cases?
Yes, it's an odd root.
Okay, good. So you've got to be comfortable with that because remember that, for example, the cube root of w cubed is w. That's true. That's good. But what about, say, the 8th root of w to 8? Is that w?
Negative.
It's the absolute value of w. Because remember that there's a parity issue going on here. This happens this way in the end because 3 is odd. And this happens this way in the end because 8 is even. Which is to say that cube root is the post inverse, the left inverse of cube. It does work, but that's not true with 8s. But because 3 is odd, it does cancel. And we get this. So now the 13s cancel. And the 8s cancel. So that's good because you know that was our claim. Our claim was that this F inverse, if you wire up these two functions in this order, if you give if you do it like this, then this is what it does. It very loudly does nothing, right? It just that x just goes right on down the line. So is this enough to show that these are inverses?
No.
It's not. So now we need to do the other order. F inverse composed with F, evaluate at x. So again, writing this without the composition operator would be F inverse on the outside, F of x on the inside. Now we can consult the formula for F inverse from the previous page, like that. So I'm going to copy down that formula exactly, except everywhere that I see an x, I'm going to write a slot that I can, you know, fill in the blank. So it will be like, okay, I see slot there, and then subtract 8 all over 13, cube all that, add 14. Okay, then, so that's what F inverse does, and that's its slot. The input is f of x, so I need to write f of x here. So now that I have that nice, I can replace f of x with what it does. From the top of the page. So again, because you know, we're alleging that this F inverse really is the inverse, what needs to happen from here on? Right. Should just cancel to x. All right. So then, because of the associative property, we can drop the square parentheses. When we do that, the 8's cancel. And we have the following, that it would be 13 multiplied by cube root of x minus 14, all of that over 13, all of that to exponent 3, and then add 14. Now what?
Cancel
13's cancel. Now what? The cube and the cube root cancel? In all cases? Why?
It's odd.
It's not actually relevant this time. Why? Why does it cancel?
Is it something about the order?
It's the order. It always cancels in this order. It wouldn't matter if it was a 3 or a 30. 30 being even. It doesn't matter. Because, in fact, the nth root of w, if you compute the radical first, and then you follow that up with the corresponding exponent. So now it's radical first followed by exponent. This is always w. For any n. Any n, that is to say even or odd. So, you know, for those of you that like to be able to use the fancy math language and stuff like that, caret n, that is to say exponent n, is always the post-inverse of nth root, of nth radical. It's always the post-inverse. But nth root is the post-inverse of exponent n only when n is odd. Because in the case that n is even, you get absolute value. So in this order, it always works. Okay. Little bit, yeah. Okay, so then, okay, so the cube and the cube root cancel. Then we have x minus 14, and then add 14. The associative property says we can drop the parentheses, then the 14's cancel, and we have just x, which is good because that's what we alleged, right? So then, therefore, we can say f inverse, f superscript -1 really is the compositional inverse. Okay, good. Any question about this one? Okay, so now I want to leave us with the last kind of thing. Okay, so does f of x equal to x squared minus 9 have a compositional inverse?
No, it doesn't.
Okay, why not?
It's,
Right.
odd that-
So in particular, what's the domain of f? All reals, right? Because the domain was not specified, the domain is the natural domain of that quadratic, which is all reals. The plot of y equals f of x is a parabola. Now, and in particular, we know enough. We know that it opens up. That is to say, the lowest point, it has a lowest point instead of a highest point. It's a parabola, and in fact, we can, you know, that quadratic is simple enough that it can be factored like so, as x plus 3 multiplied by x minus 3. And that's useful because that tells you that if you plug in -3, you get 0, and if you plug in +3, you get 0. So we can easily find some points on the plot. Here's some points on the plot. If you plug in 3, you get 0 as output. If you plug in -3, you get 0. And if you plug in 0, x is 0,
You get
-9. So you get this point down here. And that's going to be the lowest point. And the parabola looks like this. So the answer to the question is no, it does not have a compositional inverse because it fails the horizontal line test. So now last remark. So fails horizontal line test, therefore no compositional inverse. The parabola is something that can't be undone in the sense of inverse. So if I give you this function, does g of x equal x squared minus 9, and then I'm going to write myself a blank, have a compositional inverse. If I write nothing in the blank, then it's the same question as above, and therefore must have the same answer. But if I write now on the interval 1 to infinity. So now, what's the domain of g? 1 to infinity, right? As opposed to the domain of f, which was all reals. So f and g are not the same function. So it's not the same question. But does g have a compositional inverse? Now the answer is yes. The answer is yes because clearly f and g are defined by the same formula. But g's domain is smaller than f's domain, which means that g, in a sense, is only part of f. So if we plot g, the strategy I'll take for sketching really, g, is I'll sketch f. So this would be 3, 0, -3, 0, and 0, 9. And I'll just give a dashed. This is not g. This is f. G is just part of that. What part is it? So if that's x is 3, then this would be x is 2, and that'd be x is 1-ish right there. So what is g then? It's plot.
Everything vertically to the right of the 1.
Everything to the right of 1. So you can think of it like we took that whole red parabola up there, and we cut it with this x is 1, and only took the piece that's on the right. And the question is still the same. Now, concerning the red bit, does that have a compositional inverse? It does. Passes the horizontal line test, and therefore, yes, there is a compositional inverse. So, to summarize this finally, if we had a vending machine, the squaring vending machine, and you saw someone come out with a 25, if it was this one, if you saw them come out with a 25, would you know for sure what button they pressed?
No.
You would not. You would not, because they could have in principle pressed -5 or 5. Or like for this one, if they came out with a 0, you wouldn't know if they pressed -3 or +3. You wouldn't know. But if this was the vending machine and they came out with a 0, would you know for sure what they pressed?
3.
A 3, because nothing else could have achieved that 0. Okay, that's it for the whole shebang. Good. So I'll see you all on Wednesday.